Hi, everyone. For those of you who have started to look ahead towards stoichiometry, which will be the subject that we are starting this week, I've had a couple people starting to look at the homework problems for that unit, and questions have come up as far as how to fill out the tables, such as in problems 20 through 23. And so I actually wanted to just go through one of those with you because this sort of problem solving technique, this sort of table, is not addressed at all in the lecture that will be up later tomorrow. But it is a great problem solving technique, just another tool, another way to solve limiting reactant problems. And so let's go ahead and just walk through number 23. Let's go through this whole problem. And so we have a balanced equation, the reaction of iron 3 oxide with carbon monoxide to produce some solid iron and gaseous carbon dioxide. And we're told that we are starting with 33.4 grams of iron 3 oxide, I'm sorry, and 47.2 grams of carbon monoxide. And so we're asked to fill out this table to determine the amounts of reactant and product. Now you'll notice that the whole table is built around moles. And so remember that is the conversion of moles and the use of moles is a cornerstone in these stoichiometry problems. And so you will almost always be converting your given amounts over to moles, and then from there converting to whatever it is you're looking for your final answer. And so what we have to do first is use our molar masses of iron 3 oxide and carbon monoxide in order to convert these given amounts, the 33.4 and the 47.2, in order to convert those given amounts over to moles and fill that into our table. And so we calculate the molar mass of Fe2O3. We find that to be 159.69. So we're going to take our 33.4 grams of iron 3 oxide divided by 159.69. And we see that we have a given amount to start of 0.029 moles of iron 3 oxide. And so that goes into our table as our starting amount of that reactant. And then we're going to do the same with our carbon monoxide. We're starting with 47.2 grams of that. And we will divide that by the molar mass of carbon monoxide of 28.01. And we find a starting amount of 1.69 moles of carbon monoxide. You'll note, and this is another key for stoichiometry problems, that in this first conversion, I'm paying no attention to my stoichiometric coefficients. Those I'm not paying attention to whatsoever at this point. I'm just simply converting grams to moles in the same way that we've done multiple times at this point. And so we just take our 33.4 grams, convert that to moles, our 47.2 grams, and convert that to moles. Now, before the reaction starts, I have no products. And so I'm going to have 0 here for both of my products. Now we have to think about the change. And this is where we have to consider our limiting reactants. And so, and again, this is a different way to think about limiting reactants compared to the way that I have presented it in lecture. But one of the ways to think about limiting reactants is that one of the reactants is going to go down to 0. The other reactant will have some left over. And we cannot go into the negative with any of our reactants. And so with those things in mind, what we have to think about is the change in moles that we're going to experience. And so if one of these has to go down to 0, and we can't go into the negative, then that shows us that our limiting reactant is going to have to be the iron 3 oxide. And our change is going to be minus 0.209 moles. So we're losing it, so we get a negative for our change. And the amount has to be equal to what we started with. And so again, we know that it can't be, let's see if we can take that out. Okay. Our limiting reactant can't be the carbon monoxide, because if we put a negative 1.69 here for the carbon monoxide to go down to 0, then that's going to put us into a negative for our iron 3 oxide, and that can't happen. So we can see that our limiting reactant is going to be the iron 3 oxide. The other way to think about it is, again, looking at sort of the way I presented it in lecture, we compare what we have to what we need. What we have is 0.209 compared to 1.69. And so we have 0.209 divided by 1.69. We have a ratio right now of 1 iron 3 oxide to every 0.124 carbon monoxides. We need a 1 to 3. And so we need 1 iron 3 oxide to every 0.33 carbon monoxide, and we don't have that. And so we can see again that iron 3 oxide has to be our limiting factor. And so that change is going to be negative 2.209. Now is when we have to take the stoichiometry into account. We have to see that for every 1 iron 3 oxide we lose, we also lose 3 carbon monoxides. And so we're losing 0.209 iron 3 oxides, and 0.209 times 3 means that we're going to lose, so it's a negative 0.627 carbon monoxides. And so then let's look at our product side. For every 1 iron 3 oxide that we lose, we gain 2 moles of solid iron. And so we're losing 0.209 iron 3 oxides. We're going to gain 2 moles of iron for every 1. So we're going to gain 0.418 moles of iron. And again, for every 1 iron 3 oxide that we lose, we gain 3 carbon dioxides. So 0.209 times 3 means that we're going to gain a total of 0.627 carbon dioxides. And now we can fill out the afters. 0.209 minus 0.209 means that we're left with 0 iron 3 oxides. 1.69 minus 0.627 means that we're left with 1.06 moles of carbon monoxide. We went from 0 and gained 0.418 moles of iron. We have positive 0.418. We went from 0 and gained 0.627 moles of carbon dioxide, and so we have 0.627 moles of carbon dioxide. So again, remember that we're all in moles now. Right from this starting point here, when we converted over to moles, we were in moles from the very beginning at that point. Let's look at this, see if we had made a mistake. Let's sort of reset this and pretend that we had thought that carbon monoxide might be the limiting factor. Let's look at why we would know that's wrong. So we're going to go ahead and reset this. We calculated 0.209 moles of our iron 3 oxide. We calculated 1.69 moles of, let me double check that. I thought that's what we had calculated. Yes, okay. 1.69 moles of our carbon monoxide. Now, again, let's just look at what these numbers would have looked like if we had thought that carbon monoxide would have been the limiting factor. So carbon, whatever's the limiting factor, that means we're going to have 0 of it left. So we could put that in here now if we wanted to. So this is, again, thinking that the carbon monoxide might have been the limiting reagent. That means that we would have lost 1.69 moles of carbon monoxide. We also know that for every 3 moles of carbon monoxide we only lost 1 mole of iron 3 oxide. We're looking at our stoichiometry here. And so if we lost 1.69 moles of, sorry, let me just clear out my calculator here so I can actually do, there we go. If we had lost 1.69 moles of carbon monoxide, that means that we would have had to have lost 0.56. And for one thing, that doesn't even give me the option here in Chem 101 of putting 0.563 in, so we know something's up there. But let's pretend it did. Let's pretend that it allowed me to put 0.563 here, which is how much iron oxide we would have had to have lost. 0.209 minus 0.563 gives us negative 0.354. And that can't happen. We can't have a negative amount when we're done. And so that's another clue that we did something wrong here. And so let's put this back in everything the way that we had it and see what we would do from there. So we said minus, where am I here? Minus 0.209, so we end up with 0, which meant that we lost 0.627, and we were left with 1.06. We had 0 of our reactants to start with. We gained 0.418 of iron, which made us left with 0.418. And so this is where we were. So this is our correctly filled out table. Our question though, so remember everything's in moles here. Our question is the maximum amount of grams. So this just gets us to our table. We want to know the grams of Fe that can be produced. And so we know that we're going to produce 0.418 moles of Fe. So we might want to just write that down because we're not going to see that on our next screen. So 0.418 moles of Fe. And so now we advance to actually being able to calculate our answer. And so based on our setup from the previous step, our table, determine the maximum amount of grams of Fe. So remember we said that 0.418 moles of Fe could be produced. So now we just need to calculate mass from moles. So we're going to take our 0.418 moles of Fe, multiply that by our molar mass of iron, which is 55.85, and we get 23.3 grams of iron. See if we're correct. Ooh, 10% penalty if we're wrong. And we're correct. Now note here, one of the aspects again of Chem 101 is that, especially these sorts of problems, is that even if you get the correct numerical answer here, if your table is incorrect in any way, you will not get the question correct. Because questions like this are, the actual numerical answer you get, frankly, isn't as important as understanding this process and understanding this setup. And so if you get an incorrect answer, then Chem 101 will, or an incorrect table, but a correct numerical answer, Chem 101 will give you that feedback. It will let you know that something in here was probably incorrect and go back to look at that. And so I hope this was helpful, but again, this is just another way to view limiting reactant problems where we convert everything over to moles and we go from there. And so if you do have any questions as you are working through these, as always, feel free to send me an email or make an appointment for my office hours and we can try to work through a couple more problems. Have a great day.